In DC circuits, resistance is usually enough to explain how current flows. But in AC circuits, voltage and current can shift in time, making circuit behavior much more complex. In this lesson, we'll learn impedance, the concept that allows engineers to describe resistance, capacitance, inductance, and phase behavior using a single framework. Impedance is the AC equivalent of resistance. It describes how much a circuit opposes the flow of alternating current, but unlike resistance, it also accounts for phase differences between voltage and current. Because AC signals constantly change with time, a more complete description is required than simple resistance alone. In a purely resistive circuit, voltage and current rise and fall together. However, when capacitors and inductors are introduced, energy storage effects cause voltage and current to become misaligned in time. This creates phase shifts that cannot be explained using resistance by itself. To solve this problem, engineers use impedance. It combines both energy dissipation and energy storage effects into a single quantity, allowing AC circuits to be analyzed using a unified mathematical approach. Impedance consists of two parts: resistance and reactance. Resistance represents real power loss, where electrical energy is converted into heat. This is the same concept already studied in DC circuits and remains important in AC analysis. Reactance represents the effects of capacitors and inductors. Unlike resistance, reactance does not permanently consume energy. Instead, energy is temporarily stored in electric or magnetic fields and then returned to the circuit. This exchange of energy creates phase shifts between voltage and current. Together, resistance and reactance form impedance. By combining these two effects, engineers can fully describe how AC circuits respond to signals of different frequencies and operating conditions. One of the most important characteristics of impedance is that it changes with frequency. In DC circuits, resistance is usually constant. In AC circuits, however, capacitors and inductors behave differently depending on how quickly the signal changes. As frequency increases, capacitive reactance decreases, allowing current to pass more easily through capacitors. Inductive reactance behaves in the opposite way, increasing with frequency and making it more difficult for current to flow through inductors. Because of these effects, the same circuit can behave completely differently at different frequencies. Understanding this frequency dependence is essential for analyzing filters, amplifiers, communication systems, and many other practical engineering applications. Impedance allows AC circuits to be analyzed using methods that closely resemble DC analysis. Instead of solving complex differential equations, engineers can replace resistors, capacitors, and inductors with their impedance values and apply familiar circuit laws. This simplification is one of the reasons AC circuit theory becomes so powerful. Techniques such as Ohm's law, Kirchhoff's laws, Thevenin equivalence, and Norton equivalence can all be extended into the frequency domain using impedance. As circuits become larger and more complex, impedance provides a practical way to predict current flow, voltage distribution, power transfer, and signal behavior without excessive mathematical complexity. In RF engineering, impedance is one of the most critical concepts because nearly every design decision depends on it. Signals operate at high frequencies where capacitive and inductive effects become dominant, making impedance far more important than simple resistance. Transmission lines, antennas, filters, amplifiers, and matching networks are all designed around impedance relationships. If impedances are mismatched, part of the signal energy is reflected instead of being delivered to the next stage, reducing efficiency and degrading performance. Understanding impedance is therefore a major milestone for every RF engineer. It forms the bridge between basic circuit theory and advanced topics such as transmission lines, microwave circuits, antenna systems, and wireless communication design. In this lesson, we learned that impedance extends the concept of resistance into the AC world by combining resistance and reactance into a single framework. Impedance explains both signal magnitude and phase behavior, making it one of the most important tools in circuit and RF engineering. In the next lesson, we'll explore reactance and examine how capacitors and inductors individually contribute to impedance. If you found this useful, like the video, subscribe, and follow for the next lesson.